We can have higher order interpolations using Newton's polynomial. We showed that linear interpolation can be misleading because it is just a linear prediction of the function. Instead of that, we can use a quadratic or second order interpolation, for instance. A higher order polynomial is better to improve the accuracy. And the second order polynomial is simply this b0, b1 x minus x0, and b1 is actually the first finite divided difference, which is this one. We already used that in the previous example as well. Then we add the second term. In the second term, we will have another data, actually x0, x1, and x2 as well. So because we have a second order polynomial, we need 3 points. And here x0, so we subtracted only x0 here. Here then we will subtract x1 as well from the x point. And b2 is the finite divided difference. And it is just the difference of the last 2 points and the difference of the first 2 points. So x2 minus x1 and x1 minus x0. We will have 3 points anyway. And the denominator is x2 minus x0 from the last to the first point. And this is the second derivative finite divided approximation, let's say. And we can, so b1 is the slope of the line of the points x0 and x1 here. And therefore the first two terms are equivalent to linear interpolation. We know that this is linear interpolation, then we add this to have the second order interpolation. And the last term introduces the second order curvature into formula, this one. We can collect the terms by stating that a0, a1, a2, x square, and this a0 means actually this one, b0 minus b1 x0 plus b2 x0 x1. We can have an alternative representation of this formulation. Instead of using this, just use this one, and a0, a1, a2 are in terms of these b's and x's. So a1 is b1 minus b2 x0, b2 x1, and a2 is b2 simply. You can use this one as well, but this is generally the demonstration because of the Newton's formulation. And we can use these, as we said, coefficient values to obtain the b values. It's pretty simple, just use them with the data points and get the result. In this slide, we have the same example that we solved in example 15.1, but now it's example 15.2, and we will apply quadratic interpolation instead of a linear interpolation. And in the formulation here, we will have 3 data, as you can see here, and we used these 2 already previously, but we want to add this into the interpolation to have the quadratic interpolation as well. And for b0, we obtain these derivative or finite divided difference results using this formulation. Simply x1 and x0 are these and the function value. So 138 minus 0, and here 4 minus 1, you can see here. And the result is 0.462981 for the b1. And b0, we know that b0 is fx0, so it's just 0. For b2, we will have this formulation, second order finite divided difference. And for that, we will use the first order finite divided differences between the points x2 and x1. This and this, 1.79 minus 1.38, minus 6 minus 4, minus this value. And we already calculated this here. So we can just simply write here. And the denominator is the last minus 1, the first, 6 minus 1. And the result is this, you can see. And let's use these in the formulation of the quadratic interpolation. Simply b0, b1 times x minus x0, which is 1, and minus b2, we calculated here, times x minus x0 times x minus x1, these values. If we calculate from here, the result is 565844. And when we calculate the true error, we know the true value of ln2 because we calculated for 2 actually. Just use 2 here to get the results. And you can see we have a better approximation, 18.4. And graphically, you can see that actually this black curve is the actual curve. And this dashed curve is the linear estimate when we use 4 as the second point. But this blue continuous curve is the quadratic interpolation that we fit here, this one. and the result is much closer to the true value, and that's why the error is better when we compare the errors we calculated in example 15.1. So quadratic formula improves the interpolation accuracy, and this is a good example that shows it. Up to this point, we showed with examples the first order and second order interpolations for using the Newton's interpolation polynomials. And now we will show the general application of the Newton's interpolation with nth order polynomials. And this is example 15.3, and we will use the same example to have a higher order polynomial actually for interpolation. And we will add a fourth point, for instance, x3 5 and fx3 1.6 for the ln natural algorithm example, and we will estimate the ln function value of 2 using a third order, a higher order from the first and second orders. Newton's interpolating polynomial we will use. So these were the existing data, and we will add this x3 5 into here. So for the general Newton's divided interpolation polynomial, our function is this actually. Now we will chop off or truncate from after the third term, and b0, b1, and b2 here, and b3 we will have. In b2 we had the first two data subtracted from x value, which will be 2 for us. And when we add the third term, this b3 actually, or the fourth term, let's say 1, 2, 3, fourth term, we will add one more data, and it is x2, and x2 is here actually the x2, or we can use this in a different way. x3 will be 5 here, we can say that way. Let me see, x3 is 5, yes, x2, or we can write it down here. So we will have x3 is 5. You can put this in an order, or you don't need to as well. 1.609 438. As we said, this data doesn't have to be in an increasing order, or doesn't have to be in a equal spaced order. It can be a random order, as you can see here. But having maybe an increased order can be a better approximation. You can try different alternatives of organizing this data. You can take this x3 as x2 and x equals 2 as x3 as well. But the example in the book used this order, so I'm using that too. So this is our third order formulation over here. Then we will have the first finite divided difference values using this. Let's use them for x1, x2, x2, x1, and x3, x2. Use this formulation, get the results. Then use these first two for the second finite divided difference values, this one and this one. So this one here, and it is between 6 and 1 actually, because the next x2 minus x0 here, and it gives us this value, as well as we will use the last two. These will be our first order finite divided differences, and this one minus this one divided by 5 minus 4, because x3 minus x1, because we have x1 here, 5 minus 4, and this is the result. Now we will calculate the third finite divided difference using the second finite divided differences. So we will use these, so this minus this one, and x5 minus 1, x3 minus x0, which is 5 minus 1. And we will do that in the next slide. Let's go to that slide and see that. If we continue to the third finite divided difference, we are using the second finite divided difference values here. This one minus this one divided by 5 minus 1, which is the fifth and first, third and zeroth actually data. And we obtain the third finite divided difference value. Now we can use these for finding the coefficients, and we will have 3 b1, b2, b3, and b0 as well. b0 is actually simply fx0, so fx0 is this, just use that. Then use these b1, b2, b3. b1 is the first finite divided difference we found previously, which is 0.46 2098. b2 we also found it actually in the previous slide. You can get it from here as this value. And b3 we obtained here. This is b3, this value. So we write it here. And the subtractions here, x0, are for the x data. So here only one, the first one. In the second order term, it's 1 and 4. Then in the third order term, 1, 4, and 6 are being subtracted from x value. So this is the function that we have, and this is the demonstration of that function, third order. It's much closer to the actual polynomial as you can see. And we have a cubic estimate. So when we write 2 into x values, we will get 0.6278686. And the true error here is reduced dramatically, as you can see, to 9.3% compared to the second order and first order errors. This is much better because in the second order it's about 18 and in the first order it is about 40, 30 and 48, if you remember. So when we increase the number of the data for the polynomials or the order of the Newton's polynomial, we will have a better approximation. The simple reason of it is that we are using more data, first of all, and we are having a better curvature that fits through the function. And you can see here also we can interpret that these three data are a little bit away from here, and when you see that, so you can see from the prediction that when we have closer data to each other, we have a better prediction over there. Here it's much closer to the black curve, you can see, but over here we have a distinct, so we have a data far away from each other. So at this region we have a little bit slight difference. So if we had a value over here, for instance, or over here, probably we will have a better estimation of this point. So when we have a large range and try to find the data in between, the error can be higher. But when we have a lower range, for example, if you wanted to predict the value here, the error would be maybe 2%, 1%. So it's much better as approximation when we have a narrower range, let's say, to predict the data.